Good morning, my name is Guillerme Guimarães and I will be presenting the compressive behavior of gyroid structures manufactured through SLM with carburizing steels, a numerical and an experimental study. So here is the agenda of the presentation. I will begin with the short motivation and introduction, then we have the materials and methods, the results, and then the conclusion. First, I would like to bring some definition of the additive manufacturing. The STM defines the additive manufacturing as a process in which the objects are built layer by layer. But they have also other definition of additive manufacturing. The first is related to the material origin. So we have powder, we have wire, and many other possibilities of the material. And we also have the power source. We can have laser or some kind of heater. The most well-known process in this scope is the fused deposition modeling because of the common use 3D printer with plastic filament. But in this work in specific, we will be working with the metal selective laser sintering, which is a process directed to additive manufacturing of metals. And here I brought some of the advantages of the additive manufacturing in comparison with the subtractive manufacturing. The first one is related, we can relate to the machine itself. By doing the subtractive manufacturing, we have the material removal, so usually it's used as CNC machining with the numerical control, and this is a highly cost machine when compared to the usual 3D printing machine that we are correctly using. As a negative side, the additive manufacturing is more related to small batches or individual parts, while the subtractive manufacturing or the conventional manufacturing can be related to mass production. But the additive manufacturing brings the opportunity to work with complex designs, such as shown in the figure on the right. We have these geometries that was not achievable by subtractive manufacturing. But the additive manufacturing still have some developments that need to be made, especially related to the material behavior. There is still a lack on the understanding of how these structures will work when applied to real world applications. And we have some tests to assess the properties. Mostly is done the compressive test or the tractive test as shown in the figure, and I brought here with this work different perspective of the compressive test. Usually we can see the compressive test being made with cubes. This is hard to compare with laminated material because usually the laminated material follows the ASTM standard, which is related to a cylindrical body. So now I will move forward to the materials and methods. The first, I would like to talk about the sample. I chose a sample based on the ASTM A9. So it's a cylindrical sample that can be compared to laminated materials. And to evaluate the lattice structures, I choose the gyroid structure. This is a proposed structure that has a higher stiffness with higher mechanical properties. So we can see on the figure on the left that we have three configurations of lattices. The first configuration is a weight reduction, less weight reduction, and we have aggressive weight reduction with a 9mm cell size. I'm only varying the cell size I'm not working with the thickness or the bias of the lattice structure. And I made a DOE, a design of experiment, with 3 repetitions of each cells, and then we will perform a numerical and the experimental study of these gyroid structures. So moving forward to the manufacturing process and the experimental procedure. Related to the manufacturing process, the manufacturing was made with this laser print 200 machine. This is a machine developed by one of our industrial partners, and basically is a laser sintering machine. So we can see here the batch that was made with the gyroid cells. And the machine parameters, it was used a carburizing steel with 200 watts laser power, and the whole process was configured with 30 millimeters of layer with 130 millimeters of hatching space, and we also have a 140 microseconds of exposure time. To analyze the mechanical behavior of this part, we cannot use the conventional stensometers or the conventional stensometry because of the complex geometries that we have to assess. So I propose a method where I made some cuts on the CAD file and measured the area that is subjected to the loading. As we can see, for each cut we have a different area. This is natural of this gyroid structure, but I choose the smaller area since this area will fail first. So with this area and the displacement of the loading cell, I can calculate the stress and the strain of the body. And here I also brought some of the machine parameters. The machine was a universal instrument machine with a 30 kilonewton load cell and 0.25 millimeters per second of movement speed and 10% of strain as a starting point. Moving forward to the finite element design. The first part of the finite element is to convert the mesh file into a solid part, and then we can proceed with the compressive test. The compressive test was made by applying a prescribed displacement and restraining the bottom of the part. And basically we have some material that applied found in the literature. So I chose the Johnson-Cook plasticity model because it's the most used for manufacturing process and manufacturing analysis due to the good plasticity representation. I have here some properties of these materials. I have to say now that this was properties found on the literature. It was not made a proper measurement of this material. Moving forward to the results found. The first result is related to the mass reduction. We can see that the lattice was effective in reducing the mass. So when comparing to the solid part, we have for the 5mm cell a 50% of reduction in mass. And we also can see, to complete this analysis, the mechanical response of each cell, of each lattice configuration, and the better response was achieved by the 5mm cell, while the worst response was achieved by the 9mm cell. We can see that the weight reduction between the 5mm cell and the 9mm cell doesn't justify because of the stress with the weight capacity that this 9mm cell has in comparison to the 5mm cell. When comparing to the 5mm, you have almost lost 50% of the load capacity, while you just reducted 19% of the mass. The numerical experiment was used to bring more understanding to the compressive behavior, and we can see that while the compression is made, it builds up some shear stress at 45 degrees, and this will be responsible to the failure of the cell. But as I said, we don't have a perfect match between the stresses measured experimentally and numerically. Moving forward to the conclusion, uh, the first conclusion is related to the weight reduction itself. It was observed that an average weight reduction of 60% of the cell. Therefore, the lattice is a effective way to reduce the mass. It was also observed that the lattice will reduce the printing time, but there is still a gap between the numerical and experiment procedures. In my case, most likely to the material properties. And the 5mm cell showed the best performance. It has reduced the weight by 50% without losing many of the mechanical properties. So thank you for the attention. This is still a initial study. So if you want to understand more or get in contact with me, I have on the screen my email and my telephone. So thank you.